In this video, I'm going to go through the process of conducting a pooled t-test for a difference in means, as well as constructing a pooled t-confidence interval for a difference in means. As with all of these videos, I'll go through once where I focus on what calculations you do. I'll look back through and try to identify a few details, some things that may vary if the situation were slightly different. And then as I did with the unequal variances video, I'm going to also explain how to compute this stuff by hand. When I go through it the first time, I'm going to do it using software. In the situation where you have full data sets, which is what we have in front of us here, you should absolutely not do what I'm doing at the end. You should not compute this stuff by hand. The reason that I go over this is that if you're only given summary statistics, sample means, sample standard deviations, you can't use RStudio directly to make these computations. All right, so let's look through our example. So a pharmaceutical company is conducting trials on a new drug meant to lower cholesterol in adult men with high cholesterol levels. A randomized experiment compares the cholesterol levels in a treatment group that has been taking the new drug with those of a control group that has been taking a placebo. The cholesterol levels in milligrams per deciliter of the individuals are listed below. So we have the levels for the control group and the levels for the treatment group. Is this evidence that the new drug helps to lower cholesterol levels in adult men with high cholesterol levels? All right, so our step 0 well, the first part of step 0, we should probably identify, is this a hypothesis test or confidence interval? We have a yes-no question. Is this evidence that this drug helps to lower cholesterol levels? That's a yes-no question. And so this is a hypothesis test. Next, we should identify what the structure of data is, what's going on in this problem. Well, we're comparing two means for the same sort of variable, right? The two variables, or it's one variable, it's the cholesterol levels of the people in these two different groups. And we're trying to compare the average of this one variable between two groups. And so this is a difference in means question. Once we've realized it's a difference in means question, we have to decide between our three procedures. So first we decide, is this data paired? And this data is not paired. That is, these values aren't in some specific order. We're told that there's a treatment group and a control group, and there's no indication at all that this value 189, that cholesterol level for that individual in the control group, is matched up with this value 171 in the treatment group, right? And it would be hard to even imagine how you would put together that sort of experiment in a reasonable way. So it's not paired data, even though in this case we'll see these data sets do have the same size. So I guess you could be tricked into thinking it was paired data, right? It's conceivable in some sense. It's not impossible, but it doesn't make sense based on what we've been told that there's paired data. So now we have to decide, is this a pooled procedure or an unequal variances procedure? And to do that, we're going to need to enter our data sets. So let's go ahead and do that. So, one second. I want to actually make sure. Yeah, here we go. I have this. I didn't want to enter it one number at a time. So let's get the control group entered. So I'm going to call this, I'll just call it C for control. And then I'll call the treatment group T. And what I need in order to determine whether I should do a pooled procedure or a two-sample procedure or a two-sample unequal variances procedure, again, I'll talk about this later, but if I'm not told which to do, I have to check two things. So I have to check the sample sizes. So here I don't want to count all these things. And so I mentioned this in the unequal variances video. If you type length of a data set, it tells you the number of things in the data set. And then if we do length t, So these both have 56, have sample sizes of 56. So we have, let's say, I'll say like n sub c equals 56. I'll use subscripts c and t to distinguish between treatment and control. So we have the same size data set. So that's one of the things we would need to do the pooled procedures. And then we need to check the standard deviations. And so the standard deviation of the control group was 18.497, and the standard deviation of the treatment group was 22.027. And these are similar standard deviations. What do I mean by that? I mean, if I look at the smaller one and I double it, it's bigger than the larger one. Or in other words, the larger one is no more than twice the smaller one. Okay, so based on this, they're equal, similar standard deviations. We're going to do a pooled t-test. All right, so it's a hypothesis test. Step one is to state hypotheses. Now, our null hypothesis is going to be that the difference in means, since I guess I listed controlled and treatment, I'll write everything in the order mu c minus mu sub t. It doesn't matter what order you write these things in, as long as you're consistent. And sometimes it can be nicer to write in a certain order. I think in this problem, it's nicer to write in this way because we're going to get, I think, positive numbers, assuming this works out how I expect. And then my alternative hypothesis, well, this is definitely going to be a one-sided alternative. This is a cholesterol drug. It's supposed to lower cholesterol levels. That means there's only one direction that is of interest to the researchers, right? If it raises cholesterol levels, that's not a good thing. That's not why you're taking this drug. We still have to determine which direction it is. So let's think about this. We're talking about average cholesterol levels. If the drug works, then the treatment group should have lower average cholesterol levels than the control group. And in other words, this difference should be positive, right? The control group should have a higher average level than the treatment group. So it's worth spending a little time on these alternatives, thinking about, what they actually should be in the context of the question. All right, so that was our hypotheses. For step 2, we need to check conditions. For randomization, the problem tells us that this is a randomized experiment. So it's not a random sample because it's an experiment. It's a medical experiment. Presumably it's volunteers. But a randomized experiment would mean that they randomly assigned people to the two groups, treatment or control. So this is a randomized experiment. So this condition is satisfied. And you should always indicate whether, you could write that it's satisfied. I'm just going to put a check mark that saves some time. But you should indicate whether or not conditions are satisfied. We have our independence condition. So what's our population? Our population, well, this drug is meant to lower cholesterol in adult men with high cholesterol levels. So that's the population that they should be studying if that's what the drug is intended to be used on. So the population is adult men with high cholesterol levels. And the condition here is that when we have one population, right? Sometimes we have two populations in a group from each. Here it's one population, and so we want our total sample size. That is the combined size of the two samples. So in this case, that's 112, right? 56 in each. I phrase this in various ways, but the population is 10 times the sample is the same as saying that the sample is less than 1/10 of the population size. They mean the same thing, right? There are certainly more than 1,120 adult men with high cholesterol. So this is satisfied. We have a much larger population than sample. And then finally, we need our condition on data. So remember, when we're dealing with these two sample procedures, it's just like the unequal variances situation. Our condition on data is the same as for a one sample t-test, but the way that we evaluate it is based on the total sample size. So our total sample size is large. Or in other words, greater than 40. This means that all we have to check for is, are there extreme outliers? And so in order to do that, let's zoom back out and go to the graph. So I'm going to create, I'll create a histogram of each of these two. So this is a histogram of the control group. I just like to look at these things. Because we're only checking for extreme outliers, it's not necessary to do, but it's not a bad thing to look at. So we have maybe a slightly left skewed distribution for the treatment and a relatively symmetric group for a relatively symmetric distribution for the control group. But what we really wanted was box plots. So let's look at a box plot of the control group. I see two outliers, but neither looks particularly extreme, right? So when we're assessing outliers, remember we have the 1.5 interquartile range rule, and that's saying that the length of the box if you kind of stack below the quartile 1 or above quartile 3, is it more than that beyond? These both actually look like they're just barely outliers. So I'm going to say that these outliers don't look too extreme, although that's a bit of a judgment call. We don't have a rule for that. And then in this box plot, we have one outlier. Again, it doesn't look too extreme. Here it's a bit easier to tell because you can see that there's a value that's a little bit greater than this outlier that's not considered an outlier, right? That's what that bottom whisker is telling us. And so this can't really be that extreme of an outlier. It's only barely an outlier. But again, that's not something that we've made particularly, I guess, particularly rigorous the way we define that. All right, so let's flip back here and then I'm gonna get rid of those annoying error messages. So our condition on data was just that there are no extreme outliers. So there are outliers, but they don't look extreme. And so I'll say this is satisfied. So all of our conditions are satisfied. All right, moving along to calculations. Whenever possible, we're going to do calculations with software. And doing calculations with software is all about being able to correctly enter the commands that give you the results you want. And really that's about being careful, right? Once you get to the point where you can get outputs, the big risk here is that if you enter wrong commands, you could get results that are a paired t-test or an unequal variances t-test. We want a pooled t-test. So let's see what we can do to get this into software. So I'll flip to where we're just looking at what I'm typing into the code. So the command is again t.test. And so I have to give it the two values. So we decided we're doing control minus treatment, right? That's how our hypotheses are stated. And so that's how we should calculate the data. I said this before, you can get away with not doing it in the same order, but then you have to constantly think about what did I do in what order? It's not worth it. Choose an order, stick with it. I need to specify, I actually don't need to do this. If I don't specify the null hypothesis, it assumes it's 0, but I worry about that, right? I don't want to assume that software is doing something. I need to tell it what the alternative is. My alternative hypothesis was less. No, wait. Was my alternative less? No, it was greater. This is why you write this stuff down, right? It's really important that everything's consistent. So my alternative was greater. And the final thing I need to tell it is that I'm doing an equal variances test. So var.equal equals true. And I'll click enter and I get this output. Okay, so I'm going to spend a bit more time on this output than I did on the other two if you've watched the paired t and the unequal variances t videos. One thing that I really recommend, so each of the t-tests has a different title. That is, the output that you get in RStudio is different. If this 2-sample t-test is what you get when you do a pooled t-test, I believe it would say a paired t-test. I think that's what you get if you do a paired t-test, and it says Welch 2-sample t-test or something like that if you do unequal variances. I think the best thing to check for your software output to make sure that you've done the right test is the degrees of freedom. So the degrees of freedom for this test, which I'll talk about more when I talk about doing this by hand, are total sample size minus 2. So it's n1 plus n2 minus 2. 100, so 56 plus 56 minus 2 is 110. So when you're doing pooled, that's what you're looking for. That's what your degrees of freedom should be. When you're doing a matched pairs t-test, you have 2 samples, but they're the same size, n, and your degrees of freedom are n minus 1. When you're doing an unequal variances t-test, unless something crazy happens, your degrees of freedom are some decimal number, right? And so the degrees of freedom is a great place to give yourself just a quick check of, did I mess up what I typed in, right? Like if I forgot to type var.equals equals true, I would get some weird number that wasn't a whole number and certainly wasn't total sample size minus 2. And I would know I messed up. I need to go back and change what I typed in. And in any case, I want to check other stuff too. I want to check, look, the alternative hypothesis, the true difference is greater than 0. That seems good. And now I need to take this output and write it down. So this output looks good. As I said before, I'm going to ignore this confidence interval stuff. I don't even know what this means. Inf, that means infinity. What's that? But I didn't ask it to do a confidence interval, so I shouldn't expect the result to make sense. What I should expect to make sense is the t-value, the degrees of freedom, and the p-value. And so I'm going to write all those things down. I'm going to leave them up here. But actually, you know what I could do? Let's do this. I won't be able to scroll. Yeah, this will. Let's do this command again so I can scroll to what I want. Yeah, so let's pull this all up at once as I copy into the iPad. Yeah. All right, so these are the things I need. So my t-value, relatively straightforward. T is 4. It doesn't really matter what I round to, right? I'm not using this for a calculation, so I'll say 4.40. One of the nice things as we get into these calculations with software is because it's doing everything at once, you're not going to get this sort of rounding error that we're often worried about. I'll write down the degrees of freedom. I'm not going to use them for anything, but it's a nice reminder. This is what I expected, right? It's total sample size minus 2. And now I'm going to write down the p-value. And we've seen some of these before. When you get this weird output that has the e minus 0.5 or whatever, that's scientific notation. And so I'm going to write it in scientific notation. This is 1.259 times 10 to the minus 5. And I'm going to write that in not scientific notation. Multiplying by 10 to the minus 5 moves the decimal place left by 5 points. So that's this number. So tiny number, right? If we're rounding to 4 decimal places like we often do, this would just round to 0. So that's our p-value. It's very small. All right, so we have our calculations. We have t, we have p, and now we can state a conclusion. And any reasonable significance level would give us the same conclusion here because our p-value is so small, but since it wasn't stated, we'll use 0.05. Since p is less than alpha, we reject the null hypothesis. So let's remind ourselves, the null hypothesis was that the means were equal. Alternative is that the treatment group has a lower cholesterol level. So we have evidence that the drug helps to lower cholesterol in men with high cholesterol. And notice, because this is an experiment, it is reasonable to state this the way I just did. That is, I implied causation here, right? I said the drug helps to lower cholesterol. That's indicating some expectation of causation. That is the drug that's doing it. It's an experiment. It's reasonable to infer that from the results. Okay, so we don't have another sentence about conditions, right? Because no conditions were violated. And so we're done with the hypothesis test. Let's move on to a confidence interval. Estimate the amount by which taking the new drug lowers cholesterol levels in adult men with high cholesterol. Now, this is an important thing. This is good in context. Yeah, you could have a drug that you showed lowered cholesterol levels, and you were pretty sure it did, but maybe it doesn't lower them enough to be worth taking, right? Maybe there's side effects to it. Maybe the amount it lowers it by isn't really going to help anybody. So estimating the amount which it lowers cholesterol levels by is important. So step 0, we're told it's a confidence interval, but the reason it's a confidence interval is because we're estimating a value. It's a numerical question with a numerical answer. And so this is something that we answer with a confidence interval. The reason it's pooled is the same as above. I'm not going to go through that again, but the decision between is it pooled, is it two sample unequal variances, is it paired, it's the same logic for the confidence intervals as the hypothesis test. So we know what we're doing. We're doing a pooled T confidence interval. Step 1 is conditions, but they're the same as above as well. I already did that. Right? The conditions for a pooled T confidence interval are exactly the same as the conditions for a pooled T test. So I'm not going to go through that again. But I will actually just mention that they're all satisfied, right? Because that does come up when we try to write our interpretation of the confidence interval. We want to add a sentence if anything wasn't satisfied. All right, step 2 is calculations. And again, it's going to be with software. Since we have the whole data set, that's what we're always going to do. And we're trying to find a 95% confidence interval. So let's go back to what I had pulled up here. So it's a bit tempting to say, oh yeah, great. We got it right here, right? This is a 95% confidence interval. It's 10.53 to infinity. But I said this when I was doing the other videos about this. When you start to use software for these computations, be really wary of output, either that you don't understand, even if you partially understand it, right? If you just don't fully understand what it's saying, be wary of that. Also, be wary of stuff that you didn't really ask for, right? It's kind of like you get an email that's like, hey, you won this contest. And you're like, I don't remember entering this contest, right? And so you don't click on the link. I don't remember asking our studio to tell me a confidence interval. And luckily our studio, hopefully, isn't trying to scam me. They've just given me some information that actually isn't what I want. So even though it says it's a 95% confidence interval, this is like an upper confidence interval. This is a confidence interval that's erring on the side of never missing low. So that is saying, like, look, if the mean's higher, we're not going to miss that. It's not really important. The important point is what we need to do is we need to ask it for what we want. So how do we do a confidence interval? It's almost the same, although of course it can't be exactly the same as what we do for the unequal variances procedure. We have to specify our confidence level. Actually, I mean, here, if you don't specify, it just tells you 95%. So that would be fine. But we definitely need to tell RStudio to do the equal variances test or equal variances confidence interval. And luckily here, even though we're not using the degrees of freedom, we can, when we're doing a confidence interval, we can confirm, that we did the correct test by looking at the degrees of freedom. And so now we have a 95% confidence interval that looks more reasonable. So I'll write that down. So it looks like our interval is, I'll round to 1 decimal place, 9.3 to 24.5. So this is the confidence interval that I got from software. And I'll point out, if it looks like confidence intervals are way easier than hypothesis tests, it's partially because all of this stuff we already did, right? If we were doing just a confidence interval, we would have had to do all of that stuff, which is a huge amount of the work. So step 3 is our interpretation. And the first part is easy. When we interpret a confidence interval, a 95% confidence interval, we are 95% confident that. And the second part gets hard with these differences. So what do these numbers mean? So we're subtracting average of the treatment group. Average of the control group minus average of the treatment group. So these numbers are representing, on average, how much lower cholesterol is for the treatment group than for the control group. So I think about it for a bit and say, okay, I'm going to make an attempt at writing a sentence and I'll edit it if I need to. So we are 95% confident that the drug lowers cholesterol levels in adult men with high cholesterol by an average of between 9.3 and 24.5 milligrams per deciliter. So I'll read back over that to make sure it makes sense. Although, I don't really know what milligrams per deciliter are. It's some measure of concentration. We are 95% confident that the drug lowers cholesterol levels in adult men with high cholesterol by an average of between 9.3 and 24.5 milligrams per deciliter. That seems reasonable to me. Again, the drug lowers, implying causation is okay because it's from an experiment. So we're done with the confidence interval. All right, so before I go into the by hand calculations, let's just go back and see if there are any details that I should talk about. So again, I said this in the unpooled video, but for the pooled video, I wanted to go a bit more in depth into when you can do the pooled procedure. So in practice, you can actually do this pooled procedure a lot more than our rules allow us to. And oftentimes we'll just say, hey, do a pooled procedure with this data, and it may not satisfy exactly these conditions, in particular, the sample sizes being equal. Oftentimes this procedure is totally fine if the sample sizes are close and not equal. For our purposes in this course, either you're told which to do, that is unequal variances versus pooled, in which case you just do what you're told, right? Or if you're asked to decide on your own, the way we'll decide is by checking, are the sample sizes equal? And are the standard deviations close in that the larger one isn't more than twice the smaller one? And if both of those are satisfied, we do pooled. If either is not satisfied or both aren't satisfied, we do the unequal variances procedure. Sample sizes is the easiest thing to check, right? Often if it's small data sets, you can just look at them. And so you might immediately be able to rule out the pooled procedure. All right, so the way we state hypotheses is exactly the same as for unequal variances, and the conditions are exactly the same too. I'll point out that the workbook lists these two things as conditions for the pooled t-test, which isn't wrong. I just prefer to push them into step 0, right? That is, and it's not wrong to actually, because the hypotheses are the same and the other conditions are the same, you can wait until step 2 to decide which procedure you're doing. I like to decide from the start. So I push that into step 0 rather than a separate condition. So our conditions are identical to the unequal variances procedure. It's not different. Software calculations, one of the big things I pointed out that I think is worth remembering, you want to make sure that you didn't get the wrong output, right? If you get a red error message, that's annoying, but at least it doesn't tell you something that's wrong, right? But there is a risk if you type in the wrong thing, you could get the output for a paired t-test or the output for an unequal variances t-test when you wanted a pooled t-test. The degrees of freedom are a great place to check that. You know what to expect for each of the different tests, what your degrees of freedom should look like. In this case, they should be total sample size minus 2. So that makes me feel good about this. Also, something that you've probably seen before, this notion of scientific notation, it trips people up, but in RStudio, when you have really low p-values, it puts it into scientific notation, so it's not writing out a bunch of zeros. In terms of conclusion, there's not a whole lot to say. Because it's an experiment, we can indicate that there does seem to be causation. And then to the confidence interval, I really don't think I have anything more to say about how I computed all of this. I already pointed out that you have to be really careful when you do a hypothesis test, in particular, when you do a one-sided hypothesis test, which this one was, the confidence interval that the software command outputs is a one-sided confidence interval, which is never what we want. Our confidence intervals are always symmetric. And so because of that, you have to retype in the command. And in general, it's good practice. Don't accept any software outputs that you don't know what they mean. Just skip over them and do it again. All right, and then finally with these conclusions, really reread your conclusion. And you might not get the phrasing perfect, but I find that rereading the conclusion, you can often change a few words around, change the order of things, sometimes even like changing the order of numbers, turning them from positive to negative, right? Here, if we had subtracted in the other order, we would have gotten negative numbers. And by saying, oh, instead of negative numbers, we can use the word lowers, that might be a good choice, right? So spend a little bit of time on your conclusion and make sure that when you read the sentence, it is a understandable English sentence, right? That it just makes sense. Even if the context doesn't make sense, right? You might know nothing about cholesterol, but you're like, yeah, this sounds like the sort of thing, I would hear in a drug commercial on television. That's what we want. We want interpretation sentences that read like real sentences, which can be tough to do with these differences. It's really hard to put things together in a nice way. All right. I'm going to dive into the calculations by hand again. I'm going to issue this warning. Do not do this unless you have to. When would you have to do this? Well, as a reminder, let's say that I hadn't given you these data sets. So yeah, I have space here to do this. So for the hypothesis test, let's say I had not given you these full data sets. Instead, I had told you, well, we already actually have a lot of this, so let's not redo anything we don't need to do. We have our standard deviations and our sample sizes. So let's say instead of telling you the full data sets, I just said, hey, here's what we got out of our study. We got, from these sample sizes, we got these standard deviations and these sample means. So we'll need to get these, right? So for x bar sub c, I don't know, I'm typing this. I realize that I got this software output for the test, and it does tell you these things as well. And then x bar sub t is 228.73. So let's say I was just given this information. I can actually compute t and p by hand. And it should be totally believable if I can compute t that I can compute p, because the degrees of freedom is just 110, right? This is something that shouldn't be too tough. The hard part is computing t, and it gets a bit tricky here. So how do we compute this? Well, so I guess I should do it in this order. So calculating t by hand. If nothing else, this video will convince you not to do this unless you have to, if you weren't already convinced. So calculating this by hand, we start by getting an estimate for what the standard deviation is. The idea with the pooled test is that we're saying, hey, it looks like these have the same standard deviations. And so our estimate for what the standard deviation of all the data sets is this complicated looking thing it's not really that bad. You can explain relatively easily, and actually I wrote n sub 1, but I'll write it in terms of c and t. So you subtract each sample size from 1 and multiply them by the standard deviation squared. And then you divide by the degrees of freedom. And this is intended to be an estimate of the total degrees of freedom of the test. Or sorry, not degrees of freedom, of the pooled variance. We're saying these things have the same variance. What is that variance? And so in this case, that would be, so NC minus 1 is 55 times, 18.497 squared plus 55 times 22.027 squared over 110. And so let's type that in. And let's be really careful here. We need the whole numerator. And so this is our pooled estimate. And you can get a quick kind of check that your answer isn't totally wrong. This number always has to be between the two other standard deviations, right? We're trying to get an estimate for what the overall standard deviation is. That is, if these things actually have the same standard deviation. And so it can't be like greater than both or less than both. That would be a really weird thing to have happen, right? And so we get 20.339, let's say. So that seems reasonable-ish, right? It's between the two. I'm not going to think about it beyond that. And now we have to calculate our test statistic. And so I do this whole S sub p part first, and then I'm actually going to calculate this other thing because I'm going to reuse it for the confidence interval. I'm going to calculate S sub p times the square root of 1 over nc plus 1 over nt. I'll point out these formulas are in your workbook at the end of section 6.1. So if you're looking for, where do these things show up, that's where they show up. And so here that's 20.339 times the square root of 1/55th plus 1/55th. So let's type that in. I'll actually just type it all out, right? We could try to simplify this first, but so I calculate this thing. This is my standard error. And so this is the standard error is going to show up in the confidence interval as well, which is why I did that. And now finally to calculate t. T is the difference in means, the measured difference, minus the hypothesized difference divided by this standard error that I just calculated. So mu naught is 0. That's often what mu naught is, but not always. And so let's remind ourselves this is going to be x bar sub c is 245.64. X bar t is 228.73. And then we're going to divide by this number that I just calculated, 3.890. And let's see what we get. Hopefully the same thing that we got using software, because that's what it should be. And I got 4.347. And I don't even remember. Is that what we got before? So it's a little bit off. And so this is, I think, due to rounding error. I probably was a little bit aggressive with my rounding partway through. Oh yeah, no, I know why. It's because, yeah, it's because I shouldn't have, I probably should not have rounded to 2 decimal places. In any case, that's not really a significant issue here. So I get something that's off a bit by rounding error, although I do wonder, what if I added some decimal places? I'm slightly worried that I made an error. I just want to make sure that, because this is disconcerting. I'm just doing a quick check over my work here. You know, it's not particularly important. I just want to make sure I haven't written anything down wrong. Yeah, so I think this was, oh, I know what I did wrong. Yeah, okay. This is, I'm making a video, of course, so I'll have to fix this. When I typed, yeah, so if we look at this stuff, I threw myself off. The 110, the sample sizes were, no, those numbers are right. I think yeah, so it was right here at the end. Good, so it's not too much to fix. Those 55s, these mistakes are easy to make, even for someone who's done this a ton. Those 55s were sample size -1. Right here, it's supposed to be sample size. So this number here is wrong. So luckily we can fix that real quick. And so I'll skim through this fast, but it's good to have. This is, like I said, this is the problem with doing stuff without an audience, to point out that you did something that doesn't make sense. So let's quickly fix that. And then we can quickly, when you make mistakes in R, I've said this before, take advantage of copy and paste, right? Don't just, it can be really, it can be really annoying. You say, oh, I have to redo all this stuff. But oftentimes, if you made a small mistake, even if it kind of compounded, right, you can go back and fix it and copy and paste stuff. So this thing was actually 3.855. So let's fix that over here as well. Let's erase our answer because it's not right. But again, I can just copy and paste this thing that I previously typed and change this to 3.855. And now I get something that's more reasonable. This makes more sense. That felt like too much rounding error to me. And so, yeah, we were only rounding to 2 decimal places. And to 2 decimal places, we get what we got up here. Or we get close enough, right? So that's what's going on there. All right, so we got 4.39 as our t-value. Now we need to calculate the p-value. That's going to be straightforward. The t-value is all the work. The t-value is the reason not to do this by hand. The p-value is not hard because, well, we have a greater than alternative, so it's 1 minus. And our degrees of freedom are 110, right? It's just total sample size minus 2. So it's not like the unequal variance situation where your p-value is just an estimate, right? This p-value is actually, up to rounding error, is exactly the same as what we would have gotten using software, right? 1.31 times 10 to the negative fifth versus 1.259 times 10 to the negative fifth. This is because of that rounding error that was introduced. Okay, calculations by hand for the confidence interval. This is just as bad, but once you've done the calculations by hand for the hypothesis test, it's not so bad because we reuse that whole denominator, right? Our confidence interval is going to be x bar c minus x bar sub t, that's our estimate, plus or minus T star times S sub p times the square root of 1 over nc plus 1 over nt. And I already calculated that whole last part. So my confidence interval is, what are my sample means here? Let's scroll back up to where we had them. They're 245.64 minus 228.73 plus or minus. We'll need to figure out T star, but this whole S sub P times all this other stuff I already did, right? That was my number that I messed up and should have been 3.855. How do we get T star? Well, if it's a 95% confidence interval, it's not QT of 0.95, right? That's the main thing to remember. It's not just that number there. It's QT of 0.975, and my degrees of freedom are 110. So let's do that. So I get 1.982. And so I can put that up here. It's kind of a side calculation. And now we'll type this whole thing in all at once. We'll do the minus first to get the left bound of the confidence interval. So I got, we'll round to the same number of decimal places. I got 9.3, which is what we got using just entering it all at once, or using, RStudio's capability to calculate this when it has full data sets. What happened there? Oh yeah, I clicked enter by mistake. Now we want the plus, right? So we use copy and paste. And again, we get, here it rounded up to 24.6. So we got, our rounding was slightly different. But again, unlike the unequal variances situation, this confidence interval will give you an exact value. That is what we're doing with software, what we're doing with hand. The reason we use software instead of doing it by hand is to make our lives quicker. Right? You could do it by hand, but it takes a lot longer. Okay, so I know that was a long video, but hopefully you watched it in pieces and only kind of looked at what you needed. Again, if you take nothing else from these calculations by hand, what you should take from them is we don't do this unless we have to. And in particular, if we have full data sets, it is far easier, even if you have to enter the data sets by hand, right? As long as they're not too big, that's often going to be faster than trying to do this whole computation by hand instead of using RStudio.